This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Felienne for SE Radio. Today with me, Veronika Cheplygina. Veronika is assistant professor at the Medical Image Analysis Group at Eindhoven University of Technology. Before that, she was a postdoc at the Biomedical Imaging Group in Rotterdam. Veronika has a PhD in pattern recognition from Delft University of Technology. Her research focuses on machine learning in medical image analysis. Veronika, welcome to the show.
Thank you, and thanks for having me. Happy to join the podcast.
Okay, so the topic of today is image recognition. And let's start off with the basics. What exactly is image recognition?
I would say it's a set of techniques based on machine learning mainly that help us analyze images automatically. Maybe another name I would use is computer vision. That's a bit broader because recognition for me really means to assign a category to an image. So for example, if you would tag a photo on Facebook with your friend's name, you've recognized the image as being that person. But you could also think about more related tasks, for example, finding similar pictures if you are searching for, let's say, clothes or cars that you like. So that would be retrieval, and that's a different type of task than recognition.
Okay, so let me summarize. There's a broad field called computer vision.
Yes.
In which there are different things that you do with pictures. And if you're recognizing a picture, then it's image recognition. And other things like suggesting similar things are computer vision, but are not image recognition.
Yes, correct.
Okay.
Perfect.
Great. So you already mentioned that this is a technique based on machine learning. We had a few episodes recently about machine learning that we will link to in the show notes. But can you explain to us how is machine learning related to image recognition?
Sure. You could think about an image recognition program without any machine learning that is just doing image matching. So, for example, it would have a set of images it knows, and then when it tries to recognize a new image, it would just try to exactly match that new image to its database.
Okay, so that would just be something like a pixel by pixel comparison.
For example.
Okay.
So that would be matching. There's no really learning going on there. And what we want to do with machine learning is that, say we have a database of cats, and we want to find more images of cats online. What we want to do is we learn from the images we have a more general idea of what a cat looks like. So even if the new image that we see on the internet doesn't pixel by pixel look exactly the same as our database, we can still learn to recognize it.
So in terms of machine learning, that would be a classification algorithm, because we have a class of things that are a cat or pictures of a cat, and it's trying to classify pictures.
Yeah,
Is
exactly.
that correct? Are there other forms of machine learning algorithms that our listeners might be familiar with? Something like clustering, for example. Is this also something that occurs in image recognition, where you would have unsupervised learning and an algorithm says these pictures are alike, even though it doesn't really know what the category is?
Yeah, that's very, very possible. So then rather than learning a model of different types of pictures you have, like cats, you just take all of your pictures and you see which of them are more similar to each other. You see if there are groups emerging.
Another term that listeners might hear here and there is image processing. Is image processing the same as image recognition?
Well, I think the two are related because you could use image processing to enhance your images somehow before you do the recognition steps. But image processing can also be used standalone if you want to, for example, if you have old photographs that you scanned in and you want to remove the stains or the wrinkles of the paper, that would be perhaps an image processing technique and no learning is being done, no recognition.
Or a filter on Instagram. Is that image processing also?
Yes and no. I think very simple filters would be image processing filters, but smarter filters, like adding something to the image that has to adapt to the shape of your face, for example, I think there's already machine learning involved, because the filter first has to recognize where your face is in the image and then kind of adapt to the picture.
Yeah, okay. So Snapchat rainbow vomit would be image processing would be image recognition rather than image processing.
I have never seen this, but it sounds like something that you'd need to at least detect the face in the image.
Yeah, it makes rainbow vomit come out of your mouth.
Yeah, that's I got a mental picture there.
It looks really nice. Okay, let's go back to more serious image processing then. What are typical questions that image recognition answers? We already talked about, is this a cat in the picture? What other bigger groups of questions are there that you can answer with this technique?
Yeah, so you can label a whole image with a category like the cat. You can also become more fine-grained. So, for example, you want to get a bounding box of where each cat in the image is, or even more fine-grained, that you get an outline of the cat. Of course, maybe for cats this is not so interesting, but for example, if like in medical imaging that I'm working in, we might want to outline different organs in medical scans, and then we would like to be very precise, so we want to have an outline rather than a bounding box. You can have more than just two categories, so rather than saying it's a cat or it's not a cat, you can assign multiple labels to the image. For example, all the objects that you see. And more recently, this is now being extended into assigning image captions to the image. So rather than just saying cat and water, you would get a label like a cat is drinking water, for example.
Yeah, and there are these websites where you can upload a picture and it automatically generates a description like that.
Yes. Actually, maybe interesting to know is that most of us are participating in creating training data for these kind of things. Because every time you label your pictures on Facebook or on Flickr, this is mined by algorithms which are learning to improve their own recognition.
Oh, interesting. So we are all helping image recognition.
Yeah, it's a type of crowdsourcing.
So we've already touched upon a few fields where information retrieval could be useful. But what are some of the fields where it has already been applied? For example, maybe some field that our listeners are all familiar with is OCR, automatically recognizing handwriting and processing that into a font, is a field where we are already very far. What are some other examples?
Yeah, so in your camera, you probably have if you're taking pictures of people, you already probably have like a little square that shows up around people's faces. So this is a face detection in action. So basically, it just searches for patches of the image where there's a face, and it shows to you the most likely candidate. So that's a two-class problem. Is it a face or not? You can also have face recognition. So if you're tagging people, Facebook might already suggest to you who the person is based on previous pictures that you've tagged of that person.
And also, of course, I'm thinking of the new iPhone that is able to scan your face and see if it's actually you. Is that related to, or is that way more advanced?
Well, it's related in a sense. I think it would look for it would use similar characteristics, but it's a different kind of problem because it doesn't need to have a big database of who it could be. Mm. It's a two-class problem of is it you or not.
Okay. And some other fields? I'm thinking security maybe is a field where we're quite far already in using images in various ways.
So handwriting recognition or fingerprint matching, and also like biometric type things like your face. I do think, I'm not an expert in this topic, but I do think these algorithms can sometimes be fooled. So if you show to the algorithm a picture or a video, sometimes they can easily be tricked into thinking it's you, but you don't have to actually be there. Categorizing images that you upload to apps. So for example, I recently was selling some things in my house, and I think I sold some shoes. And when I uploaded the picture, that's the first step you do. The online marketplace app, Marktplaats, it was already suggesting to me that I should put this in the category shoes. Also, for example, apps for beer and wine, like Untapped for beer and I think Vivino for wine. You can scan the label and then it matches it to a database. So this is a bit more like the matching problem. But of course, because you take the pictures at a different angle and different lighting, it's a bit more advanced than just matching pixel by pixel. Well, I've mentioned already medical imaging that I'm working in. So we have different tasks, like for instance, just segmenting an image into different parts, like different organs. So this is creating outlines of each organ. Or we can think about more diagnostic purposes, like detecting potential abnormalities, which then would be shown to an expert. Of course, self-driving cars need to understand what they see, so they need to have a pedestrian detection and a car detection, interpreting road signs, which would also be more like a matching algorithm. Yeah, there's a lot of things. I think in most things you can think of how to apply such an algorithm.
Yeah, if you think about the possibilities, you're seeing the world yourself all day. So everything
Yes.
you see, I'm just looking around in my house. I'm like, oh, an algorithm could recognize if the curtains are open or if my door is locked. There are plenty of possibilities. Okay, we talked about fields where image recognition is applied now, but what are some fields where you think it's going to be applied soon or it could be applied soon?
Yeah, so there are, I think, pretty cool things, both good and bad. So right now, when the algorithms are learning, they get a pretty good idea of what the underlying structure of the images is, so they're able actually to generate more images that look like that. So if you show it tens of thousands of cats, it can create more cats. There's even a website, I think we can find it for the show notes, where you draw an outline of a cat and it fills in kind of the colors by itself based on what it's learned. And it knows where to put the eyes and everything. Yeah, you could do pretty scary things with this. So if you would be able to put faces of some people on some other people, you could create all sorts of fake news that would look realistic, or revenge porn. Yeah, I think many other probably not very nice consequences.
So you see more dangers in the generation of these fake images, put together cats, then you see opportunities to do good.
Well, I'm not sure. Maybe it's what's more talked about in the news right now. If you read sort of about the dangers of AI, etc. But yeah, I can think of also of some nice applications. So, for example, if I'm buying clothes, I would ideally like to have an image generated of how they would look on me, without having to buy them first and then send them back. Or a really cool thing happening in medical images is that we can learn to synthesize one modality from the other. So we can, for example, synthesize a CT, so a CAT scan from an MR scan, which is very good because in MR it's safer, and CT you get a dose of radiation, so you cannot always do that, for example, for babies. So that would be really cool if we can learn to generate one from the other.
So you can convert one image that is less precise to a more precise or a better image.
Yeah, because right now MR doesn't see everything that we need, but there might be hints in there which we do not see, but which with learning, so you would need coupled MR and CT scans. The algorithms can learn to fill in those missing details.
Oh, nice. So that's a really positive application of the generation of images rather than the recognition of images.
Yeah.
Okay, so now we're all very excited about the applications of these techniques and we want to get started. What are some of the core principles that you need to learn about in order to be able to use image recognition yourself? What do we need to know?
I think the most important thing is how you want to represent your images. What I mean by that is Well, images they come in all sorts of sizes. And so let's take as an example, let's take apples and pears. Let's say we want to recognize fruit. So how this was done traditionally is that we would think of some visual features that for us can represent this fruit, and that would help us discriminate the two.
So you would think form for apples and pears.
Yes.
Shape.
Yes. So for example, for the apple, you could measure its length in different directions, and it would be symmetric. And the pear has different lengths in different directions. So those would be two high-level features which we thought of because we know how apples and pears look like. And based on just that, maybe we can already do a good classification.
And then, just to help me understand, the high-level process would be, I have a lot of pictures, I define a feature that I want to look at, the shape and the length and the height ratio. I transform the pictures into a list of height and width, and then I'm going to do the classification on that list, and not really on the pictures.
Yes.
So there is an extraction step, and then there is the real machine learning step.
Yeah, exactly.
Okay,
so that would be
it.
Feature extraction. Then you put each image into what we call a feature vector. So that's just some numbers which represent that image. So like shape. And then on those feature vectors, we can train an algorithm to distinguish different categories. More recently, though, this has been moving. So this is a really high-level representation of the data for which you need some kind of prior knowledge about apples and pears. But if you have some data that you don't really know what the things are that you're looking for, you have to think of other ways to extract this feature vector. And more recently with deep learning techniques, this is now being done more or less automatically from the data. So it takes as a representation just the pixels and learns by itself what patterns of pixels to look at which are discriminative for the classes in the data.
So maybe not all our listeners are aware exactly of what deep learning is. Is there an explanation for what exactly deep learning is?
It's just a type of machine learning, and the deep refers to that when you combine these pixels in different ways, there's several steps into it. And these several steps, this refers to the deep.
Okay,
part.
so rather than the one feature extraction step we had before, now there are multiple steps in the process.
Yeah.
Okay, got it. What are some of the issues or common problems that we could run into? So suppose we have this apples and pears data set, or we have cats and we want to know how to make more cats. What could possibly go wrong?
I think a problem that happens very often is overfitting. What this means is that you have had too little data to learn the true patterns in it. So say you're learning to distinguish cats from dogs, but you have a very small data set taken of your own pets in your house. It could be that the algorithm then learns to actually detect your couch, because your cat always sits on your couch, and not actually has learned the cat representation. It will always learn something, and it may seem correct if you test it again on your own photos, but if you would test it on photos of cats and dogs in the real world, it would do very poorly.
And that is what overfitting means, that the algorithm is very much tied to the data and isn't applicable to a bigger, different data set.
Precisely. So it has overfitted and it has not generalized.
Are there other issues that we could run into?
I think this is really the main one. How you could try to overcome this, of course, gathering more data, more diverse data. So cats from different cameras, different types of environment, and also when you're developing your algorithm, you have to make sure you're not secretly cheating yourself. So you would have training data on which you develop the algorithm, and test data on which you test how it does. But if you do this multiple times and you notice that the performance on the test data is becoming better, you're kind of tweaking the algorithm and you're going through the steps several times. Although you're using two data sets, training and test, which looks like you're doing things correctly, you're actually overfitting yourself on the data you have seen.
Got it. Okay, so suppose we want to apply this in a business setting, because the examples of the cats may be a little bit for fun. What type of business problems are suitable? How do we know how to recognize a problem where image recognition might be of use?
Yeah, so let's say if we focus on categorization problems or recognition problems, you would need to think about the kind of categories you have, how many are there. So is it recognition problem like binary, like is it this or no? Or is it a very large set of categories? So the first one is simpler than when the number of categories is large. You should also think whether what you think makes for similar images or images of the same category, if that's based more on visual characteristics of the image or more on some kind of higher level idea. For example, if I'm working with images of people, face detection, our faces look different, but there are very common characteristics in each face, that there's a round head and there's two eyes, etc., etc. Faces from not faces is easy, but let's say you would be interested in faces of actresses from faces of not actresses. This is a much more difficult problem because actresses come in all shapes and sizes and non-actresses come in all shapes and sizes. So that knowledge is not really in the image.
Yeah, then you would need external data like IMDb, for example. A big data set of who is an actress. Would that be feasible?
Yeah, I think so. But then you don't learn from the faces how to generalize to, let's say, new actresses.
Yeah,
of course you could overfit by detecting the red carpet behind the actress
and the beautiful gowns.
Sure, it's not something I think we can encode.
Yeah, so the same goes for business problems. We have to think: is the thing we're representing really visual? Or is it something that has different meaning? Like maybe you can determine between a good product and a broken product, but it would be harder to distinguish between a new product and a returned product, because people could return it because it's not broken, also because they don't like it, and then there's no visual similarity.
Yeah, that's a good example. Yeah.
Okay, thanks. Of course, we've talked about it a lot already. There's not just the algorithms, there's also the data. So suppose we want to apply this in a business context, what type of data do we need?
You would like ideally your data to be representative to what the algorithm will encounter in the real world. And you want to have as much data as possible to learn a good model that generalizes and that doesn't overfit. So for example, if you're interested in doing kind of security and recognizing who is where from a security camera, it would be difficult for the algorithm to train it on like passport pictures of those people, because that's just like one view with very nice lighting, and in the test environment it would be black and white, very pixelated photos. So then it becomes harder.
Yeah, so it has to be realistic, not just of the topics, because a passport photo would be realistic of the person, but it has to be realistic of the setting. Is there any sort of feeling you could give us for the size of the data set? When do we have enough data for image recognition to make sense? 10 pictures? 1 million pictures? 1 billion pictures? Is there anything that makes sense as a number?
Well, I would say 10 is probably definitely too little, but during my PhD I've worked with datasets that were less than 100.
Okay.
It also depends on how difficult the task is, in the sense of, are you learning some simple visual features, or is it a more high-level thing? And also on how many categories you have. So for 2 categories, maybe 100 pictures is okay if you're learning to distinguish cats from not cats. But if you want to describe all the objects in the image, then of course it will not be enough. So computer vision datasets now I think have at least 10,000 images, probably 100,000, 1 million. That's more the size. And I think the the state-of-the-art algorithms now, they're trained on this kind of web mined data, which you and I have helped annotate as well.
But even still, you're saying that there's some hope for people that work maybe for a small company or medium-sized company. We don't all have to be Facebook and have to have that much data in order to be able to do some image recognition. Maybe with 100 or 1,000 pictures, if you were doing simple things, it's still a possibility that lies in our realm of.
Yeah, definitely, I think so. Especially if you have quite a concrete problem that you're solving. What's also popular now is that these deep learning networks, which learn, so they need the most data. So these deep learning networks that have learned to recognize general everyday objects, to take those networks and to kind of not train the algorithm from scratch, but train it from the point that it has already learned what kind of visual features are important in images in general. So these networks kind of already know that edges usually mean that one thing stops and another thing begins.
So they can build upon each other's knowledge.
So that's something called transfer learning. So like rather than training the algorithm from scratch, you are taking skills it already has and applying them elsewhere. So sometimes I use an example of hockey. If you have played soccer before, then you don't have to, although the rules are different and the game is different, there are some general principles that apply as well. So you're not starting from zero.
And this would go for pictures of hockey and soccer maybe as well. If an algorithm knows where to find the ball in soccer, it might be useful to use that knowledge to find the puck in hockey or the ball in hockey, because it would be on a similar place between people on the ground or in the air. Cool, that's a really nice example. Also, in between, you mentioned that deep learning algorithms need the most data. Why is that? Is that because they're unsupervised learning?
There's an unsupervised and a supervised part, but let's maybe not get into that detail. But because they need to figure out kind of from the bottom how to combine, how to weigh the different pixels in the end to get to the category label.
Yeah, it's because they don't have the feature.
Yeah, they don't have this high-level knowledge that we gave them from the start. And actually now it's they can still overfit even with lots of data. So there are some examples now online where these networks have learned to recognize, let's say, cats and dogs. But you can fool these networks by changing one pixel in the image, and then the label that the network gives changes, even though for us, of course, it would never happen. And the funny thing is that with these, let's say, traditional features, which are sort of out of fashion now, this would have never happened because the pixel is exactly the kind of noise that those high-level features learn to ignore.
Yeah, like the shape of an apple. If there's one green pixel outside of the apple, then
nothing would happen.
Nothing would happen. Okay, so the deep learning isn't all hallelujah fantastic. There are some intricacies still there also.
Yeah, exactly.
That's good to know, I guess. So what about the resolution of pictures? Suppose we want to do something again in the context of our own companies. Do we need great pictures from the newest iPhone, or could we also do useful things with old phones or security cameras, things like that?
I think many things are possible. I think mainly I work on images which are not that modern and high resolution and color.
Again, it mainly depends on what you want to do with it. Security footage is fine if you want to analyze security footage, but not if you want to do radically different things.
If you have some representative data that somebody has labeled, I think you can definitely do things.
Okay. Talking about labeling, what are some issues that the data could suffer from? Do the labels always need to be perfect, or is it okay if data is mislabeled here and there? How do you handle the data when you're working with the algorithms?
Yeah, so often it is indeed assumed that the labels are perfect. I think most algorithms can deal with a certain amount of noise as well, but it's not unlimited. So when a photo that we clearly think is a cat but it's labeled as dog, and we're teaching somebody else, we would clearly say, oh no, I cannot use this as a training example. But for the algorithm, it's all the same. So at a certain point, if many images are mislabeled, it's garbage in, garbage out, I guess.
So do you manually sample the data set before? Is this something that people do, or they just assume it will be fine, and if it's not, they look at the data then?
Well, it depends where your labels come from, right? So it's possible that you hired some students to label the data. It's possible that you put the data on Amazon Mechanical Turk and you underpaid people at, I think it recently came out, $2 an hour to label some images. Yeah, depending on
the context and the application.
Yeah.
How do you know what the algorithm is paying attention to? And here, of course, we're specifically talking about the deep learning techniques. If you don't have the features, is there some way to get the features back from the deep learning algorithm that it can tell us, well, I know it's a cat because it has 2 eyes and a nose? Or is this information hidden in the network, but in a way such that we mere humans can't understand it?
Yeah, you can visualize in the image which pixels are receiving high weights.
Okay.
So if it's indeed cats, you would see that, and if it's learned to recognize cats correctly, you would perhaps see that those pixels are more important. But I think if you're learning sort of more difficult concepts, your detections will not necessarily make sense. So if you're learning that you are on a beach, so you would need several things for that. You would need to see some sand, probably. You need to see some water, maybe some people in bathing costumes. So then I'm actually not sure what would happen. It's not like there's one thing in the image that makes it that category.
Yeah, and there could be features also with a beach, the horizon and things that aren't necessarily just one pixel, but more a shape in the picture, like a feature. Okay, so sometimes we know and sometimes it's a bit more vague.
Yeah, and you would still, I think, need to encode, although the promise is, okay, with deep learning you can completely learn everything from the data, I think you would still need to encode how large is the area that you're looking for approximately. Yeah. So if you're looking for this like one specific object, like a cat or something more general.
Yeah, or a picture of a beach, which would essentially be the entire picture because...
Yeah, or that you would need to pay attention to multiple regions for the label to be correct.
Okay, so suppose we do want to get into this. Are there any programming languages or systems that are more suitable or very useful, or will any programming language do?
I think with most languages, if you have to use that language because that's the language that everything else you're doing runs on, I think it should be possible.
No, but suppose we have a greenfield project and we can pick whatever is best according to you.
Then I would say probably Python is the most popular choice because, you can... It's open source and there's many toolboxes and tutorials on how to use it. I actually use MATLAB most of the time for, let's say, historical reasons because of medical imaging, and it's just very nice for rapid prototyping, but it's not something that I would use if I were building software that had to work on a mobile phone, for example. So it also depends on where you want to deploy the algorithm.
Yeah, sure. And talking about those libraries where you mentioned that they are available, for example, for Python, is it easy or advisable to use different libraries? Or would you say that it's not that hard and it's better or easier to build systems or algorithms yourself?
Yeah, there's a bit of a trade-off there. I would definitely advise for, if you want to build something that is robust, to rely on existing libraries. At the same time, I think it's good for, if you're trying to understand what's happening under the hood, to try to build a few simple things from scratch. So for example, like this feature extraction and a simple classification algorithm, so you kind of see what the algorithm is doing and what goes wrong.
And this is really a possibility. I mean, it's not way too hard to build an algorithm like that.
No, I think it should be okay. I mean, you need an example that's that's been worked out before by somebody. So you know it is possible to recognize the things.
And there are, I think, some websites where there are already data sets of pictures and labels that you could just use and play with, right?
Yeah, so a common one, I'm not actually sure where to download it, but we can look it up, is the NIST digits. So these are just OCR digits from 0 to 9, and you have to recognize which digit it is. So this is quite often used for education. And there, of course, it's also nice because you can actually look at which pixels it's paying attention to, so you can see what's going wrong.
Nice. We will make sure to look up the link and add it to the show notes.
Yeah.
Any other data sets that we could play with?
There are a few computer vision ones of recognizing everyday objects. ImageNet is one, Pascal, and there are a few others which are acronyms. So I'll have to Google those.
No problem. We'll put them in the notes as well because it's probably exciting for our listeners to try their hand themselves with some data sets that are not too complicated, and as you were saying, that you know that it's possible, because sometimes some things like, is it a lamp or a cactus, maybe it's just too hard and it's impossible to try that. So that's probably not a good first data set.
And for if you want to try further, there's Kaggle. So their machine learning competitions are hosted. So it's not only images, it's also other data sets.
But there we are less certain that it could work, right?
Although during the competition you will already see the leaderboard of results. So you will have some idea of how possible it is. And there's even a website with medical imaging datasets. If somebody wants to try that, it's called grandchallenge.org. And these are public datasets of, for example, CT scans or MR scans, and the tasks are to delineate organs or to detect certain diseases.
Yeah, because of course you yourself work in the medical world where you use image recognition in medicine. Can you talk a bit more about that? Why is medicine so suitable, and what are some of the problems that you are solving yourself?
Yeah, so again, there are different types of tasks, as I just mentioned. So like delineating things in the images, like organs.
And this is making the outline delineating?
Yeah. So this is also called segmentation.
Okay.
There's more detection. So you would try to detect possible tumors or possible lesions. So these would be candidates. So you would try to find bounding boxes around suspicious spots. And then, of course, you want to detect more. You want to detect more than there really are. You don't want to miss any.
Oh, yeah. So you want to err on the side of having too many positives rather than missing one. Yes.
Exactly. So then you would have all these candidates, and then maybe you would have an expert go through them and say this is a real candidate and this is not, and then you would do a second step of classifying the true tumors or lesions from the incorrect detections.
Okay, but you envision that there would always be an expert in the process, or do you think in a future people just go into a scanner and the result comes out without any doctor present?
No, I don't really see that happening. I don't see now articles about AI replacing doctors, but I think there are so many tasks which really need to be automated and are not yet. So there are still plenty of doctors, PhD students often, who are delineating things in the images which should really be done by an algorithm. And I mean, this is not a diagnosis. This is just seeing
auxiliary.
Yeah. So, for example, if you want to measure different parts, you want to outline them in the image, and this an algorithm can do. But there's no decision making there, like it means the person has a disease or not.
But do you think this is for ethical reasons, or do you just think that algorithms are not good enough ever to be able to see the things that our human eyes can see?
So you mean why it's not
entirely automated
now being applied in practice?
Yeah, no, why we can't envision a future where it would be entirely human out of the loop and just the algorithm. Is it just impossible because we will always see tiny things that an algorithm can never pick up on?
No, I do think that also, of course, algorithms can see things that we cannot pick up on.
Yeah.
And also can take into account much more data. But I think there will always be things that the algorithm hasn't adapted to, like a disease that has mutated and then nobody has seen it before. I mean, the algorithm will kind of be forced to give an answer based on the categories it knows to give. And while it's not that the human doctors will know from the first time what it is, but I think that's kind of the distinction, that once the machine learning system has learned something, that's kind of its world, and it cannot go further to new problems. So then if the doctors would have to invent something else, and this is what people have been doing so well for all of history. And some people, I think Elon Musk believes algorithms will do this, but I don't.
Yeah. Yeah, this is of course something you hear in the news all the time, like AI is going to replace whatever profession inserted in the headline.
No, while it's still possible to fool algorithms with a single pixel, I don't have those fears.
Yeah, that's good, I guess. At least for your career, it's probably good if you aren't made obsolete by algorithms. If just you are replaced by algorithms, that would be a bad thing. So let's talk about performance, because if we think about algorithms, at least if I think about algorithms and machine learning and deep learning, I think, this is going to be computationally expensive. Can these algorithms run on your laptop or your mobile phone, or do you really run them on a big cluster or somewhere in the cloud? How does that work?
I think for the things I've worked on, I've never had really too big data, especially with medical images. We often have the problem that we have too few scans to analyze. There's also the distinction between training the algorithm and testing it. So training and learning the model can take quite a long time, but then the testing, so when you have some new data you want to categorize, that is usually actually quite quick. There's not so much computation that still needs to be done. It's just you take the pixel, you go through the pixels, you use the weights, combine them, and out comes a category, let's say.
So the training is expensive, but actually classifying one single image isn't very expensive.
Yeah, I mean, I wouldn't say that holds for all the algorithms, but
sure,
you
but
can.
In general.
Yeah.
We just want to get an idea of whether or not it's applicable and what type of things we need to think about, like investing in hardware. So you're saying if you just take a picture with your phone and want to have it classified, that's not necessarily going to take a long time. It's just the pre-work that is going to be potentially expensive.
Yeah, and now I think also there are techniques, if we are to build an image recognition, that it doesn't, for example, go patch by patch from the top left corner of the image asking, is this what we're looking for? And then moves a pixel, is this what we're looking for? I mean, there are smarter algorithms now that can do this. And I think these are also included in some toolboxes.
Yeah, this is what I wanted to ask about, actually. If we have huge images, maybe, I don't know, pictures that the Hubble telescope takes, do you break them up in pieces? But I think what you're saying here is you wouldn't break them up in little small pieces, but rather you would scan them and zoom in on a certain region and then analyze that. Am I understanding that correctly?
Yeah, I was thinking about just more general photos before, because you mentioned the mobile phone. With really large images, I'm not sure. It depends. So if you're doing a detection problem, so let's say you are detecting some new galaxies or in these large images, if it doesn't matter what's in what one part of the image to detect something in another part of the image, you can of course just split the image up and process it and parallelize the processing.
Yeah, if they're unrelated, like different stars, and you're not looking for a galaxy but just separate stars, yeah, sure, then you could split it up.
Yeah.
Yeah, but assume we're looking for one or multiple related things, then you say that there could be techniques that just scan the image, maybe take a few pixels to see where it could be.
Yeah, I think that should be possible.
Okay. Well, this is good to know for people that work on large sets. We've already talked about algorithms, we've talked about data, but how will we learn this? Suppose many people in our audience are normal programmers and they want to learn more about using image processing or image recognition. What are some skills that you need to know? Do we need a PhD in data visualization like you, or what do we need to learn?
I think it's good to have some intuition of these feature vectors. So how an image looks like, and what happens if you take what you think are similar images and you represent them by some numbers.
And how would you get this intuition? That's just trying it out.
Yeah, exactly. So for example, like with these NIST digits, with these
The OCR
0
data.
to 9,
Yeah.
because then you can see what the algorithm is paying attention to. You can see whether the digits you thought were very similar actually have similar feature vectors, and so can be easily classified by the algorithm.
And how would you see that? You would use some sort of data visualization on the feature vectors, I guess.
You could cluster them in a 2D or a 3D space.
Oh yeah, that makes sense.
And because they're little square pictures, often people also actually just put the picture onto the plot. So you would see, okay, so here are the zeros grouped, and in some other region of the plot, the ones are grouped.
Oh yeah, I can
Or you could
visualize
use
this.
different colors. That's maybe applicable for all sorts of data.
Okay, so I'm going to classify that as sort of a practical data analysis skill, that you have some intuition for what your data is doing.
Yeah.
Of course, these things, for me, I only have a PhD in software engineering, so for me already these things are sort of scary. It's algorithms and mathematics and linear algebra. Do I need to learn about new mathematics, and if so, what type of things do I need to learn about?
No, you wouldn't need to learn really new things. Maybe some understanding of statistics helps. So, like I mentioned before, that cats are often on couches. That's a correlation of things, but you don't need to be able to derive lots of things on the board. And also some idea of optimization, function optimization, or linear algebra. So
what is function optimization?
So the algorithms, they when they have training data, they try to make as few errors as possible on this training data, given the categories. And this error that the algorithm is making, it's a function of how well it is doing. So what the algorithm is actually trying to do is to minimize, to find the minimum of this function. So that would be the parameters with which the algorithms makes the least mistakes.
Yeah, that is as close as possible to the real data set. Yes.
And well, of course, if you have a convex function, which means it's like really nice and smooth, just like a bowl, or like a hill.
X squared.
Yeah, like x squared. If you have a convex function like that, you can just calculate its minimum, so you don't need to do anything complicated. But the functions that these algorithms optimize are unfortunately not so nicely shaped, so they have all sorts of bumps, and you need other techniques for that. And you also have to be aware that it can find a local minimum, so the algorithm thinks it found a good solution, but in fact there are better solutions elsewhere.
Yeah, that could be related maybe to the overfitting.
Yeah, for example, also.
Got it. Okay. That sounds like it might be doable for, let's say, normal people. Where would I learn this? Can you give us a few resources where to learn more about image recognition?
There's a great machine learning course on Coursera by Andrew Ng. So I think that's actually how Coursera started. This was the first course he developed, and only then Coursera happened.
Yeah, that's the massively popular course.
There are different tutorials depending on which language you would like to use. So there are some for Python and for MATLAB that I know. I think also on YouTube you can often find talks of people demonstrating some application there. They are doing like tutorials as well. But I think Coursera is a great place to start.
Do they have a course specifically about image recognition also? Or would you just say do the machine learning course and that's applicable enough also to images?
Yeah, I haven't. I do think they have something more now. There are also some courses on deep learning, but I haven't done those, so I'm not sure whether to recommend those. But I think the machine learning course is a great start.
Okay, thanks a lot. Is there anything else you wanted to share? I think we've covered a lot about image recognition, the algorithms, the data, the skills, what to do. Is there anything you wanted to add to the show?
Yeah, maybe I'm thinking what my take-home message is. That would be to always be skeptical about your algorithm and look at your data and look at the mistakes it's making, because you might be overfitting without knowing it. Hide some data from yourself to test your algorithm.
Oh, I like that. That's a very concrete tip. You just hide a little bit of data. You don't take it into account at all, and only once you've designed an algorithm that you think you're happy with,
exactly,
you bring out the data.
So you can see how well you really did. How well you really did.
Yeah.
Also, I think don't believe many hyped articles about how algorithms are taking over the world. It's pretty hard to build robust algorithms, as we've seen with the pixel example.
Yeah, so you really see them as an aid to people, but not a replacement of.
No, definitely. I think it will replace some very boring jobs which exist right now. I also, if I have to sort my photos, I mean, I know I could build an algorithm, but there isn't something that just very quickly does the job for me, like a paperclip that says, oh, I see you're putting the pictures with these and these people together in a folder, maybe because it's their birthday. Shall I help you find all the other pictures of this person? I mean, I would really like that, but it's not there yet. So no, I think people shouldn't be scared for their jobs.
Okay, well, let's end on that positive note then. Veronika, thanks a lot for being on the show. We will make sure that we add all the things you promised in the show notes, and also a link to your blog, and because you're an avid blogger, and your Twitter profile, so people can learn more about all the exciting things you're doing. Thanks for being on the show.
Thank you.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.